Peterson Manufacturing presents Understanding LED and Incandescent Lighting. Back in 1945, when Peterson first started manufacturing vehicle safety lighting, the technology was pretty crude. Stoplights and clearance lights were metal housings with plastic or even colored glass lenses. Sealing was usually limited to a felt gasket or rubber O-ring, if there was any at all, and they all used incandescent bulbs, which has been the traditional way of creating electric light for 130 years. An incandescent light is pretty simple. In its most basic form, it's just a piece of metal wire, usually tungsten, which burns at a very high temperature. If you supply an electrical charge, the metal's resistance will generate heat. If you supply enough electrical current, that electrical resistance will heat the filament to its combustion temperature, generating a large amount of energy in the form of both light and heat. But not for long. Once the filament burns up, the show's over. But we want the light to last more than a moment, and we don't want a flame. What we want to do is slow the burn down. Fortunately, there's a way to make that happen. As your 7th grade science teacher taught you, oxygen is necessary for combustion to occur. If we prevent oxygen from getting to the filament, we inhibit its ability to burn. A bulb is simply a glass barrier between the filament and the environment. It contains a partial vacuum, or sometimes an inert gas. What's important is not what's in it, but what isn't in it. Oxygen. Well, at least not very much. When the electrical current heats the filament past its burn temperature, without the oxygen necessary for the filament to burn outright, the reaction is slowed and the filament glows brightly as it is slowly consumed over many hours. Significant heat is still generated, but there's no flame. The filament is still burning up, but it's burning in slow motion. Today, a technological revolution is underway. Incandescent bulbs are giving way to light-emitting diodes, or LEDs. Look at these two marker lights. They look almost identical, and they perform the same function. But the one on the right uses LEDs instead of the incandescent bulb in the one on the left. The advantages of LEDs are dramatic. LED lights last 10 times longer, and since they generate very little heat, they're much more energy efficient. They light up quicker too. Once energized, incandescent lights must reach the filament's burn temperature before they emit light. But LEDs light up almost instantaneously, as much as 0.2 of a second quicker than an incandescent bulb. An LED consists of a tiny silicon chip that radiates light when a current is supplied. LEDs are normally encased in plastic, but unlike an incandescent bulb, the plastic barrier does not enable the chip to function. Rather, it just protects the fragile LED from breakage or corrosion. A light-emitting diode is a very sophisticated device. That sophistication makes the manufacturing much more challenging than making incandescent lights. Compared with the traditional light bulb, a single diode is more expensive and does not generate as much light. So what's in that little silicon chip? Well, there are two different special types of silicon, P-type and N-type. When electrified, light is generated where the two different substances meet. The chip doesn't burn, it just gives off light at a specific frequency, that is, a particular color. That color frequency is determined by the dimensions of the materials. So, to review, incandescent bulbs convert electricity to heat, which causes combustion, which generates light. LEDs, on the other hand, skip the whole combustion part of the process and simply generate light directly from the electrical current. The trade-off is that LEDs produce less total light over a much narrower wavelength spread. The most common LED configuration is known as the T1 design. This is the typical dome-shaped LED you see used in all sorts of inexpensive consumer appliances. Today, most vehicle safety lighting uses more advanced surface mount LEDs, and the newest, highest power LEDs utilize special form factors that extend the life and functionality of the diode assembly. Your 7th grade science teacher probably also taught you about Roy G. Biv. Red, orange, yellow, green, blue, indigo, and violet. The spectrum. Red is the longest wavelength of the visible colors, violet is the shortest, and all the visible wavelengths of light in equal intensity, make white light. This graph shows the light produced by an incandescent bulb. You'll notice that it generates approximately the same amount of light energy throughout the spectrum. It appears white. As LEDs were developed, scientists and engineers had a much easier time generating useful amounts of radiant energy below the visible spectrum. The earliest LEDs developed in the 1950s emitted radiation only at infrared frequencies, wavelengths too long for the human eye to see. Even today, some of the most popular LED applications use diodes that generate invisible infrared light, such as those in your TV remote. The first commercially available visible light LEDs could generate only red light and didn't put out much light at all. It was just a happy accident that automotive engineers had long before chosen red and amber as the standard colors for vehicle taillights and marker lights. If this hadn't been the case, LED vehicle safety lighting wouldn't have been practical as early as it was. Once manufacturers such as Peterson found that enough LEDs clustered together could generate the light necessary to meet legal requirements, the first LED safety lighting products appeared on the market. Today, individual LEDs are much brighter than those of just a few years ago, which is why a lower number of diodes is now common in safety lighting. The first red LEDs were developed in the early 1960s, but yellow LEDs didn't appear until a decade later. By that time, red LEDs were 10 times brighter. The development of new LED designs has been a progressive march up the color spectrum, from red and amber to green and blue. Total light output continues to increase across the board, but higher frequency LEDs remain more expensive and less bright than red LEDs, and all LEDs are still restricted to a narrow slice of the spectrum. You may be thinking, hold on a second. White LEDs are becoming popular. They must emit light over the whole spectrum, right? Well, yes and no. There's still no LED that naturally emits white light, but we can trick a blue LED into emitting white light by surrounding it with a special photoluminescent phosphor. This coating absorbs light of one frequency and emits it at a different, lower frequency. When the light emitted by the phosphor is combined with that of the original blue LED, the resulting light approximates the appearance of white light. However, since the phosphor surrounding the LED blocks and absorbs a portion of the blue LED's output, we actually end up with less overall output. Furthermore, the phosphor increases the LED's operating temperature by converting a portion of the absorbed light into heat. And heat is electronic components' number one enemy. It should be obvious that the chemical makeup of the phosphor material must be carefully matched to the underlying LED. Less phosphor allows the overall output to be brighter, but more blue. This is why the brightest white LEDs tend to have a bluish cast. Vehicle regulations restrict how much blue tint a light can have and still legally be defined as white. It takes a lot of careful chemistry and physics to create a white light LED that is truly white, truly bright, and designed to last. This is why white LEDs have only recently been produced commercially in large numbers and remain more expensive than colored LEDs. Really bright white LEDs, such as those suitable for vehicle headlights, remain a major engineering challenge. Every vehicle safety light, LED or incandescent, sits behind an optical lens of some sort. In many ways, the engineering behind this simple piece of plastic is as important and as vital as the complicated light source behind it. Since incandescent bulbs generate white light, the lens colors the light by permitting only part of the spectrum to pass through, absorbing the other colors. Since LEDs generate colored light at the source, the lens doesn't need to filter the color of light, but lens design is still important for LED vehicle lights. The lens is shaped to direct the light in specific directions. Vehicle regulations dictate the lighting pattern of different vehicle lights, such as brake lights, marker lights, and backup lights. Where they must project light, where they can't project light, and how much light they can emit in any particular direction. The proper lens design has a great deal to do with whether any light, LED or incandescent, meets those regulatory requirements. So, With all we know about LED and incandescent vehicle safety lighting, let's compare the two. LEDs last longer, are more durable, and use less energy. Incandescent lights? Well, they're cheaper to purchase, but that's not always an advantage. Truck fleets that switch to LEDs end up saving money, even though the lights cost more to buy. The higher cost of LEDs is offset by their longer life and greater efficiency, so they're cheaper over the long haul. That's not to say that incandescent lights won't be around for a while. They still make sense in some applications. Unlike the lights on commercial trucks that are in service constantly, incandescent bulbs might last for years on recreational equipment, such as a boat trailer that only makes a short trip to the water a couple of times a month. In this case, the extra expense of LED lights might not be recouped over the expected life of the vehicle. The purchase price of the vehicle also helps determine what lighting is appropriate. Percentage-wise, the higher cost of LED lights would have a much greater impact on the price of that $1,000 boat trailer than the price of a $100,000 tractor trailer or piece of construction machinery. And finally, a burned-out taillight is more than a nuisance for some. A company's reputation may be at stake. LEDs are safer. Their quicker response translates into faster reactions, and as much as 16-foot shorter stopping distances by drivers following an LED-equipped vehicle. Fewer burned-out taillights means not just lower maintenance costs, but also a better chance that vehicles will arrive at their destinations on schedule. Given all that, it's easy to see why most professionals believe that LEDs are worth a few extra bucks.